The Big Bang is the definitive narrative of modern cosmology, a bold declaration that our universe had a beginning and has a finite age, just as the humans who live within it. That finite age, in turn, is defined by the evidence that the universe is expanding. Those two ideas, a singular cosmic beginning followed by billions of years of cosmic growth, are so strange that some people have never made peace with them. As a result, skeptics have been questioning the validity of the Big Bang model for as long as there has been a Big Bang model. Among mainstream cosmologists, doubts about the Big Bang largely melted away in the 1960s with the discovery of the cosmic microwave background, an omnidirectional buzz of radiation that makes sense only as a relic from the hot early era of the universe. But around the fringe, the doubts have persisted, and lately, they have intensified, inspired by groundbreaking discoveries made by the James Webb Space Telescope in the early universe. In a stunning observation, NASA's time machine, the JWST, has just detected an unimaginable mass of galaxies at the edge of the observable universe, challenging the Big Bang, our supreme theory about the origin of the universe. Is it time we must completely change our view of the cosmos and our own existence? The answer will be revealed in today's episode of EYES 200M. The idea for the Big Bang first came about back in the 1920s and 1930s. When we looked out at distant galaxies, we discovered something peculiar. The farther away from us they were, the faster they appeared to be receding from us. According to the predictions of Albert Einstein's general relativity, a static universe would be gravitationally unstable. Everything needed to either be moving away from one another or collapsing towards one another if the fabric of space obeyed his laws. The observation of this apparent recession taught us that the universe was expanding today, and if things are getting farther apart as time goes on, it means they were closer together in the distant past. An expanding universe doesn't just mean that things are getting farther apart as time goes on. It also means that the light existing in the universe stretches in wavelength as we travel forward in time. Since wavelength determines energy, shorter is more energetic. That means the universe cools as we age, and hence, things were hotter in the past. Extrapolate this back far enough, and you'll come to a time where everything was so hot that not even neutral atoms could form. If this picture were correct, we should see a leftover glow of radiation today in all directions that had cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background in 1964 by Arno Penzias and Bob Wilson was a breathtaking confirmation of the Big Bang. It's tempting, therefore, to keep extrapolating backwards in time to when the universe was even hotter, denser, and more compact. If you continue to go back, you'll find a time where it was too hot to form atomic nuclei, where the radiation was so hot that any bound protons and neutrons would be blasted apart. A time where matter and antimatter pairs could spontaneously form, as the universe is so energetic that pairs of particles and antiparticles can spontaneously be created. A time where individual protons and neutrons break down into a quark-gluon plasma, as the temperatures and densities are so high that the universe becomes denser than the inside of an atomic nucleus, and finally, a time where the density and temperature rise to infinite values as all the matter and energy in the universe are contained within a single point, a singularity. This very final point, this singularity that represents where the laws of physics break down, also is understood to represent the origin of space and time. And this was the ultimate idea of the Big Bang. Of course, everything except the last point has been confirmed to be true. We've created quark-gluon plasma in the lab. We've created matter-antimatter pairs. We've even done the calculations for which light elements should form, and what abundances during the early stages of the universe are. And we've made measurements and found that they match with the Big Bang's prediction. Coming forward even further, we've measured the fluctuations in the cosmic microwave background and seen how gravitationally bound structures, like stars and galaxies, form and grow. Everywhere we look, we find a tremendous agreement between theory and observation. The Big Bang looks like a winner. But the universe, as we see it, has some properties and some puzzles that the Big Bang doesn't quite explain. If everything began from a singular point a finite amount of time ago, you'd expect different regions of space would have different temperatures, since they wouldn't have had the ability to communicate and exchange particles, radiation, and other forms of information. Leftover particles, relics from the earliest, hottest times, such as magnetic monopoles and other topological defects, and some degree of spatial curvature. Since a Big Bang that arises from a singularity has no way to balance the initial expansion rate and the total matter and energy density so perfectly. But none of these things are true. The universe is the same temperature and properties everywhere, with no leftover high-energy relics, and is perfectly spatially flat in all directions. Either the universe was simply born with these properties for no foreseeable reason at all, or there is a scientific explanation, a mechanism that caused the universe to come into existence with these properties already in place. On December 7, 1979, physicist Alan Guth had a spectacular realization: an early period of exponential expansion that preceded the Big Bang, what we now know as cosmic inflation, could have caused the universe to be born with all of these specific properties. When inflation came to an end, that transition should then give rise to the hot Big Bang. Of course, you can't just build an extra idea into your old theory and declare that your new one is better. In science, the burden of proof on the new theory is much more severe. As a result, the doubts have persisted, and lately, they have intensified, inspired by groundbreaking discoveries made by the James Webb Space Telescope in the early universe. In just its first year of scientific operations, the $10 billion U.S. infrared telescope has delivered stunning views of the nascent universe, finding large numbers of surprisingly bright galaxies that existed at a time when the cosmos was in its infancy. With its 6.5-meter mirror, JWST was designed to investigate this early era, which was mostly out of reach for its predecessor, the 2.4-meter Hubble Space Telescope, HST. Observations thus far from the JWST have simply astonished researchers and left them trying to digest exactly what they were seeing. According to the standard model of cosmology, after the fiery Big Bang some 13.8 billion years ago, the universe cooled, and energy turned into matter that eventually coalesced during the first few 100 million years, forming the first generation of stars and galaxies. Astronomers thought they had a decent understanding of this process, but JWST's initial results may suggest that stars and galaxies were forming far faster than anyone expected. The telescope had done nothing less, read the headlines, than break the universe and appended models of cosmic history. Subsequent data from the JWST have ruled out some of the more dramatic findings, and new simulations can accommodate at least a few of the strange observations. But some bright, massive, and early galaxies continue to confound theorists, suggesting that our understanding could shift in the coming years. No data at the moment has broken the universe. says Priyambada Natarajan, a theoretical astrophysicist at Yale University in New Haven, Connecticut. But I think there are interesting potential tensions emerging on different scales, Natarajan said. Resolving these tensions will require researchers to revisit their fundamental assumptions about galactic evolution. That could mean bringing new ideas to the forefront while leaving others in the cosmic dustbin. But note that this is not the first time that we have spotted the two early galaxies. In May of 2009, astronauts installed one of Hubble's final and most important instruments, known as the Wide Field Camera 3, WFC-3. It vastly improved the telescope's ability to see in infrared. As the universe expands, traveling light gets stretched out to longer wavelengths or the redder portions of the electromagnetic spectrum, so the oldest entities can't be seen in the shorter ultraviolet or visible wavelengths. WFC-3 allowed Hubble to capture the light from several record-breaking objects, including the galaxy GNZ11, which existed when our universe was only 3% of its current age, or a mere 400 million years old. Yet Hubble never found much from this early epoch. Were the few visible big, bright galaxies due to limitations in the observatory's instruments, or were astronomers witnessing the very beginnings of galaxy formation? Once JWST launched in December 2021, scientists swiftly dismissed the latter possibility. Two teams spotted the galaxy class Z12, about 50 million years older than GNZ11. Other JWST observations showed staggering numbers of galaxies potentially existing as early as 180 million years after the Big Bang. There's a lot of galaxies that are bright enough for us to detect with the JWST, says Jehan Kardelteep, an astrophysicist at the Rochester Institute of Technology in New York. We knew there would be some, but people were surprised at how many there are and how easy they were to find, he said. These galaxies are also potentially more massive than cosmologists expected. The scorching conditions in the first few 100,000 years after the Big Bang meant that matter couldn't settle down and condense into entities such as stars and galaxies. As the universe expanded and cooled, standard cosmological theories hold that particles of dark matter, mysterious stuff that outweighs normal matter about 6 to 1, clumped under the force of gravity and formed massive halos. These then gravitationally attracted regular matter, which slowly accumulated in the halos and produced the stars and galaxies we see today. Most models estimate that